Hello everyone, welcome back. Here's vanAmsen. Today we are going to tackle an intriguing problem from LeetCode, problem number 808, titled subserving. So this problem is a medium difficulty level and it involves concept of dynamic programming, probability, and recursion. So what's even more interesting is that it has a surprising twist, which we will discover as we dive deeper into the problem. So let's get started. The problem goes as follows. We have two types of soup, type A and type B. And initially we have n milliliter of each type of soup, and there are 4 kinds of operation to serve the soup, and we stop once we no longer have some quantity of both type of soup. And our task is to return the probability that soup A will be emptied first, plus half probability that A and B become empty at the same time. So the challenge is to find an efficient way to compute this probability given the constraints of the problem. So now let's move on to our approach to solve this problem. So we will use a top-down dynamic programming technique commonly known as memoization. So the goal is to calculate the probability of soup A running out first, considering each possible state of soup A and B. So first we will address an interesting property of this problem. So when n is greater than 4451, the probability that soup A will be emptied first approaches 1. So to optimize our solution, if n is greater than 4451, we return 1 immediately and avoid further computation. So you might be wondering, but from where did you get 4451? It's a great question, and we will get to that later in the video. So next, we will scale down n, and the serving size in the problem are multiple of 25 milliliters. So we divide n by 25 and round up to the nearest integer. So now n represents the number of servings of each soup rather than the quantity in milliliters. So and then we will define the state of the system as per. So AB, where A denote the remaining amount of soup A, and B indicating the remaining soup of soup B. And each state corresponds to a unique scenario with a specific remaining quantity of soup A and B. So let's implement it. First part, so if n greater than 441, we return 1, n greater than plus standard unordered map int double memo and return dp n mem. Okay, so here we have first part, and to prevent redundant computation, we use memoization, and this involves storing the result of each state in a dictionary, and after it's computed for the first time, if we encounter a state that's already been calculated, we can simply retrieve the result from the dictionary instead of recomputing it. So let's implement further. So private double dp ab unordered map int double memo, and if ab less than 0, return 0 half, and if a less than 0, return 1. If b less than 0, return 0. And int key will be a times 500 plus b, and count memo key, return memo of key. And memo key will be 0.25, and -4, -3, -1, -2, -2, and -1, and return memo key. Okay, so here we have it. Let's run to verify I didn't make any typo here. small n. Okay. I mean, small n, or here we can have big N. Okay, so it looks like everything's good. Yeah. Okay, so now to the explanation. So what we did. So finally, we formulate a recursive function to compute the desired probability. And this function takes two parameters, so A and B, representing the remaining quantities of sup A and B, respectively. And the function first checks if the current state is in the dictionary. If it is, it returns the stored result, avoiding redundant computation. If not, it calculates the result based on served scenario. So if both sups are empty, if only sup A is empty, if only sup B is empty, and if there are remaining quantities of both sup. So let's dive into the code now. And in C++, we start by defining our class solution, and then a function subserving if n is greater than 4451, we return 1 immediately, and we then scale down by of factor 25, and also initialize memoization map memo. And we then define a private function dp that takes the remaining quantities of sup A and B and the memoization map as a parameter. So it returns the stored result if the current state in memo is calculated, and otherwise that's where the logic happens. So why this? So because we have only 4 options, so each option could have 25 probability. And why dp? Because we recursively track the portions, and as you can see, if we have -4, so here is -4, and here we have minus 100, because this operation will deplete 100 of sup A. So this is remaining sup A, sup B, and if you see, like 100 divided by 25 will be 4. So that's why it's -4, because it's minus 100 milliliter of sup. And other is 0, so we have here 0. And here we have -1 and -3, and it's correlate to here. So you can see that we have -25, -75, and here -50, -50. So that's why -2, -2. So -2, -2. So it's the third case, and here we have 75, 25. So obviously -3 and -1 for B sup. So B and A. And yep, we have -3 and -1. And here the probability, because it's one of the case, so probability that sup will deplete, it's just 1. Because we have depleted, so it's partial result. And otherwise, for example, for B, we have 0 probability, because we are asked about sup A. And in this case, sup B was depleted first. And here we have half probability as for task requirements. So there we have it. So we can run it also for unseen test cases to verify everything work. So yeah, our implementation is quite optimal, and it beat 100% with respect to runtime, and also 65% with respect to memory. So I hope you enjoyed this problem. And we use dynamic programming and probability and recursion to come up with an efficient solution. And remember, yeah, the number 4451. It was derived empirically using a binary search limit method, which is an efficient way to find exact threshold where the result of subservings become n. So basically, how I found it. So I implemented this code previously in Python, and also check using a binary search to optimally solve limit from lower n of 1000 to upper limit of 5000. And because in task description is that answer could be provided 10 to the power of minus 5. So 10 to the power of minus 5 is my epsilon. And basically, if we use the rounding to 5 decimal places, 4451 will become 1. So there is no need to count for numbers greater than 4451. And yeah, I tested empirically using binary search. So yeah, but basically you can test every possibility and round it to the 5 decimal places and see where this function gets to 1. So there is no need to count for upper functions. So I hope you so this solution is now more clear to you. And as always, thank you for watching, and happy coding. And don't forget to like, share, and subscribe to stay updated with our latest coding challenges. And I will also post in the description link to other solution in C++, C#, Python, Java, JavaScript. Yeah, thank you for watching, solving and exploring, and see you next time.